Alright, in this section here we're going to be talking about linear functions. Now we talked about what a function was in the previous section, and we looked at a set of ordered pairs, and we were able to tell by looking at the set of ordered pairs if it was a function or if it was just a relation. But in this particular case we're going to be talking about linear functions. So if you can remember, we had talked about linear equations. For example, this is a linear equation. But if we want to talk about a function, we can actually give the function a name and not write it as an equation here, but we can write this using this type of notation. And of course f is kind of overrated, and so is x. We can name our function anything we want. Sometimes we name them g. G of x is equal to, let's say, 3x plus 3. Okay? Or we can name it h of x. And I'll give this one, make this one look different. How about just h of x is equal to 2x? All right. We could name it m. M sub x is equal to, let's say, a half x minus 1. So this reads m of x. Okay, m of x. Now this guy right here, we don't have to use x every time. For example, we can use a t. A lot of the times if we're talking about time, we use a t plus 1. We can call our function k, and our independent variable is t. Alright, let's see, we can add functions. I don't know, should I even talk about this? If I said k of t and m of t, we can add our functions together and get a new function. We'll call it p of t. Alright. Sometimes when we first start about learning about functions, we might talk about what's called a function machine. And I don't know, it's good to always put some kind of picture to this abstract idea. We'll call our function f, and all the things that go into the function is our domain, and stuff that comes out of our function is known as the range. Remember, this was talked about in the previous section. So let's say, for example, in this particular section here we're talking about linear functions. So let's say we define f of x as, we'll define it up here, f of x is equal to 2x. So let's see, you know what, let's end our domain will be, let's say the domain's the set of natural numbers. So in other words, 1 goes into our function, goes in there, what do you think comes out? 2 times 1 is 2. So 2 falls out. 1 goes in the machine and 2 comes out of the machine. Let's say, let's put another number in there. Let's say 2 goes in the machine. So 2 goes in, machine does its thing, and out spits what? 2 times 2 is 4. See that? So this is known as our function machine here. So things that go in is the set of, is our domain, and things that come out is our range. Isn't that neat? The function machine. Do all kinds of stuff with that. You don't have to put numbers in the function machine. You can put just any kind of object in there, and whatever comes out, right, is in a range. Now, if I were to put 1 in the machine and 2 came out, but then you can't have 2 things come out of the machine at one time, or that's not a function, remember? So remember, in the previous section we talked about what not a function was. In other words, you can't have an ordered pair. I guess I'll write it right here. You can't have two ordered pairs, okay, with the same first coordinates, because that's not a function. So in other words, if I put a 1 down in here, I can't have 2 and 3 come out, right? Only one thing at a time comes out. Okay. Well, that's the idea of the function machine, and you can expand on that if you would like. But we're gonna move on now with we're gonna touch on some graphing some functions. So I'm going to start with something like this. F of x is equal to 2x, and we want to graph this on the Cartesian plane. So I'm going to roughly sketch this thing, and first we'll do a table here. Okay, this is my independent variable, and then my dependent variable is my f of x, which we define to be 2x. So I'm just going to pick some points here and plug them in. For example, plugging -1 in. So -1, 2 times -1 is -2. And then we're going to plug 0 in to our function. I should say this is f of -1 is equal to -2. And of course, plugging 0 in, you get 0 out, and we could say f of 0 is equal to 0 out, right? 2 times 0 is 0, and let's say 1. We plug 1 in, so this would be f of 1, and we get 2 out, as you can see. So we come over here and we graph this. So when I plug 0 in, I got 0 out. Let's use a different color here. Okay, I plugged in 1 and I got 2 out, so we'll say this is 1 here, and we get 2 out, so we'll say this is 2. And then I skipped one, -1, plugging -1 in, you get -2 out. We'll say -2 is down here, so -1, -2. Now of course our range, or I'm sorry, our domain is R, that boldface R here. That means all real numbers. And so that means that we can plug in, we're plugging in every single point on the number line. So what we can actually do here is kind of connect all those points. So pretend that we've done all those, and of course that goes to infinity in that direction and so forth. Now, the domain of this function is all real numbers, and the range, remember these were all the y values out. So if this is going to infinity, then that means that for every x value there's going to be exactly one y value, but there's going to be all the y values. So the range is also R, but actually we would say it's from -infinity to +infinity, and we could say that the domain is from -infinity to +infinity. So this is a set of numbers here. It's an interval, and -infinity, right, is going off in this direction, and +infinity is going off in this direction. So we're going to talk about the domain and range a lot in probably the next 10 minutes or so, as we give some examples and do some more graphing. But let's actually graph this using a graphing utility. Okay, so this is Google's graphing utility. You can type this in the Chrome browser's address bar, 2x, and this should come up. So look, we got a nice little slider here. So let's see, we plugged in 1 or something like that, and we got 2 out, and then plugged in 0, 0, and then we plugged in -1, and we got -2 out. As you can see, here's my coordinates here. The question is, what happens when I add a 2 or a 1 on the end of this, 2x plus 1 or 2x plus 2? How's that going to affect this graph? Well, I messed around over here with the zoom trying to get these two guys about the same distance, and it's looking like it's not letting me do that over here. So this is as close as I can get. So the scale doesn't look like it's 1-to-1 at all. Looks like this distance is a whole lot greater than this distance here. But that's okay, you get the idea. Now let's, man, there's just a lot of things to talk about here. I think I was saying, what happens if I added a 1 onto this? This would be 2x plus 1 or 2x plus 2. Well, let's find out. And it looked like it rescaled it again. Let's see, I want to zoom out on the x-axis. So let's try to get as close as we can. Well, as you can see right here, the graph moved up, it looked like 1 unit. It moved up 1 unit. Let's add I added 10 to it this time, and of course it rescaled itself again. Okay. Well, what happens to the graph when you add a number onto the end right here? It moves the graph up. Where this graph is crossing right here, this ordered pair is known as the y-intercept point. So that would be 10 or 0, 10, and this is known as the x-intercept. So this is known as the y-intercept. The y-intercept is 10, and the x-intercept is, what is that, -5 it looks like, maybe. The x-intercept's -5. The y-intercept, if I said the y-intercept point, then that means that we must include the order pair, which is 0, 10, and then this down here would be the x-intercept point, which is going to be -5, 0. So we're going to need to know how to find the y-intercept and the x-intercept. We're going to need to know how to do that. All right. Well, let's graph some more of these guys. Okay, in this particular one here, look, we just got a horizontal line because we have y is equal to 5, and so we just have a horizontal line. Isn't that interesting? So no matter what I plug into this function, you're going to always get 5 out. Now I know this is written as an equation here, but we can also consider it a function, even though it's not written as f of x is equal to 5. But let's actually go to the whiteboard. Okay, so this might actually sound kind of confusing, but if I had f of x is equal to 5, no matter what I plug in here, we still get 5 out. So it doesn't matter. You could plug in a -100, right? We still get 5 out. Doesn't matter what we plug in for x, we're still going to get a 5 out, which means we have a horizontal line. Okay, let's look at this one. I have -2, or -x plus 2. And as you can see, the line decreases as we read this from left to right. What's happening to the line here? It's decreasing. Let's take a look at our y-intercept, which is 0, 2, and where it crosses the x-axis, which is about right there, which is going to end up being 2. It's going to end up being 2, 0, right? Should be. Anyway, for x-intercept, remember what the point is. That's actually writing the ordered pair. X-intercept point, the y-intercept point. Alright. The domain, okay, the domain's the set of all real numbers, or we could say from -infinity to +infinity. And the range of this function, let's just zoom out. As you can see here, the range is just, these are all the y values. So, this line's going on down here forever. You're going to, right, for every x value, you get a corresponding y value. Okay. So the range of this function is from -infinity to +infinity, and remember, the range is the y values, and the domain is the x values here. Okay. And if we're talking about points, it'd be the first coordinate and the second coordinate.